Welcome to a lesson with Dr. Powell. Let's take a look at the idea of a potential function and how it can help us to evaluate, that is, a line integral. So suppose that we have a point P and a point Q, and we have a path C1 and a path C2, two different paths that link P and Q together. Now, let's also suppose that we want to take the line integral of G along each curve. And further suppose that the curl is 0. Now, if the curl is 0, that means that if we were to reverse the path of C2, so it goes this way, and we go C1 then the reverse of C2, we get a loop around a region here. And since the curl is 0, taking a double integral or over this region or a surface integral, we end up getting 0, which means that the sum of the line integrals this way plus that way is 0. Well, if you change the direction, it just makes it negative. So the negative of the line integral of this guy plus this line integral would be equal to 0. That actually means that if we put the direction back here, the line integral along C2 will be equal to the line integral along C1. They'll be the same. That means in general that we can define a function where we could let P be constant. I just chose this arbitrarily, but it could be anything. And let Q be a variable. Then you can, let it have coordinates X, Y, Z. Then we can well define a function, X, Y, Z, that what it does is it takes the line integral of G from P to Q, and it doesn't matter what path we use because all paths will give the same thing. So really, this is all we need to define this function, just like this. Now, what does that mean in particular? Well, for one thing, I mean, what if we had a path that was only going in the X direction? Then what we would have in that particular case, if we're just going the X direction, that F would end up just being the antiderivative in the X direction. Similarly for G and for H, it would be at least an antiderivative, it being the output of this definite integral where this bound is variable. And so what we end up getting is that if we just took the gradient of F, we would get back to the derivative in the X direction, the Y direction, and the Z direction. They would just be these right here, the things that we need to integrate to get back to F. So that means in particular that the vector field G, which is FGH right here, is just the gradient of F. So F will serve as a potential function. And we call it a potential function here, and it represents, and it gives us a way of simply just treating normal line integrals as you would for finding an antiderivative. So in particular, all you need to do if you wanted to, we start with G and we find a potential function for G such that its gradient is G itself, then if we want to find a line integral of G along some path, all you have to do is take your whip your potential function out, F, and then put in the endpoints and subtract just as you would for normal integration. Kind of nice how we just turned line integrals into just a simple take an antiderivative, plug in, where this is just a function. In fact, it's just a function with one output, which makes it really nice. So in this particular case, Q minus P would work just great. This right here is actually going to be equal to either of these. Kind of nice. All we need to do then is to be able to find this potential function. We're guaranteed that this potential function exists, as we've discussed, if the curl of the vector field is equal to 0. Thanks for watching.